Amid the scorching heat of the driest place on Earth, Cerro Dominador rises from Chile's sea of sand like a pinnacle of engineering. It is Latin America's first solar thermal power tower, a concrete spear piercing the sky at a height of 250 meters, surrounded by an entire energy field of nearly 10,600 mirrors that simultaneously directs sunlight toward the top of the tower, raising the temperature there to around 560 degrees Celsius to generate electricity. But how can this harsh desert be transformed into a power plant capable of operating even after the sun has set? And how did engineers lift a 2,300-ton steel structure hundreds of meters into the air, while below, two enormous tanks hold tens of thousands of tons of molten salt? Today, join Mandarin Tech as we step inside one of the world's harshest mega-project construction sites, peel back each layer of its machinery, and witness how humans created a second sun in South America. Located near the town of Maria Elena in the Antofagasta region, this massive complex was created to redefine the limits of renewable energy. Instead of using a parabolic dish, the system employs a large field of mirrors to concentrate sunlight onto receivers at the top of the tower, where solar energy is converted into electricity at a scale of several megawatts. At the heart of the project is a concentrated solar power system with a capacity of 110 megawatts. Below it, steel tanks, pumping stations, pipelines, steam generators, and turbines form the rest of the machine. Each component performs a different task, but all of them must connect with precision-like gears within the same system. Thanks to its sophisticated thermal storage mechanism, the plant can keep the turbine operating and continue feeding electricity into the national grid for 17.5 hours after sunset. This machine has transformed the scorching heat of the daytime into a gigantic energy reserve, powering hundreds of thousands of homes with the sunlight of the previous day. To transform the empty stretch of sand into a massive construction site, surveying teams first had to establish a strict coordinate grid. Every element, from the batching plant and access roads to the power and water systems, was arranged around a single focal point: the location of the tower. Once the coordinates were locked in, heavy equipment began lowering the site to the required elevation. Unsuitable soil layers were removed, making way for a massive reinforcement cage interwoven with numerous utility conduits and embedded connections. Pouring the foundation concrete required strict temperature monitoring. The curing reaction caused the core of the foundation to heat up rapidly. If the outer surface were suddenly cooled by the desert weather, the entire foundation block could crack before it was ready to carry any load. Once the foundation reached sufficient strength, the tower shaft began to rise using slip-form technology. A continuous formwork system enclosed the structure, while workers continuously tied reinforcement, formed technical openings, and pumped concrete. As soon as each concrete layer became strong enough to hold its shape, hydraulic jacks lifted the entire formwork system upward, repeating the cycle until the tower shaft was completed. At the top of the tower, a steel and concrete load-bearing platform was constructed to support the receiver and keep it precisely aligned with the center of the heliostat field. Inside, the tower gradually became a vertical technical shaft containing maintenance platforms, elevators, stairways, electrical cables, and sensors. Most importantly, two molten salt pipelines ran through the tower. One carried the salt upward to the receiver, while the other carried the heated salt back down at around 565 degrees Celsius. Because the metal continuously expanded and contracted under heat, the pipelines were mounted on sliding supports, expansion joints, and controlled anchor points. Finally, each pipe section was welded, cleaned, and pressure tested. Temperature, pressure, and flow sensors were also installed along the lines, forming a monitoring network for the molten salt. Right at the base of Cerro Dominador, engineers began assembling the most important component of the entire system: the receiver, standing about 32.4 meters tall, equivalent to a building of more than 10 stories. The entire assembly process took place at ground level, so that welders, cranes, and inspection equipment could access it easily. Once completed, the structure weighed approximately 2,300 tons. The receiver was transported to the opening at the base of the tower, rotated into the correct orientation, and aligned with the lifting shaft. Steel cables were connected to the lifting points, load sensors were activated, while above, 16 hydraulic jacks simultaneously took on the weight. The lifting operation proceeded at a speed of only about 5 meters per hour. After each cycle, the system stopped to check cable tension, tilt, and the condition of the anchor points. As it rose higher, the margin for error became increasingly narrow. When the receiver reached an elevation of 220 meters, engineers aligned it centimeter by centimeter, matched the support frame with the structural platform, and gradually transferred the entire load away from the cable system. After dozens of hours suspended inside the tower, the 2,300-ton structure finally stood in position, ready to receive sunlight from the heliostat field below. Once the receiver was completed at the top of the tower, work shifted to the heliostat field. At the Rio Glass Solar Chile factory in Antofagasta, the mirror panels were manufactured before being transported to Cerro Dominador. Each heliostat uses 32 mirror panels, forming a reflective surface of about 140 square meters. The steel frame, drive system, and mirror panels were then assembled into complete units. At the assembly area, the steel structure was mounted on supports, while the dual-axis rotation mechanism, control box, and sensors were installed at the center of the frame. Each mirror panel was positioned, leveled, and secured. After inspection, the heliostats were transported to the construction site, where more than 10,600 support foundations had already been positioned across a heliostat field covering more than 700 hectares. Cranes lowered each unit onto its support, locked the connections, and connected the electrical and data lines to the control center. During the peak construction period, local female workers made up about 33% of the workforce involved in manufacturing and installing the heliostats. But in the Atacama, dust rapidly accumulated on the reflective surfaces and directly reduced the amount of sunlight reaching the receiver. Specialized cleaning vehicles therefore moved between the heliostat rows, using rotating brushes and treated water to clean the mirror surfaces. Each heliostat consumed about 45 liters of water in water-saving mode and up to 100 liters when heavily soiled. The final step was calibration. Each mirror rotated toward a test target, cameras recorded the reflected spot, software measured the error, and the rotation angle was adjusted accordingly. From thousands of separate components, a vast sea of mirrors gradually took shape, and all of them were ready to face the same point at the top of the tower. While the heliostat field gradually spread across the desert, 2 enormous steel tanks were also constructed at the base of the tower to hold about 46,000 tons of molten salt. The tank foundations were reinforced and covered with heat-resistant materials, after which steel plates were assembled and welded together to form the bottoms and walls of the tanks. On the outside, thick insulation helped minimize energy loss. Pumps, valves, heat exchangers, and pipelines were then connected to form the circulation loop. Salt from the cold tank was pumped up to the receiver, heated to around 565 degrees Celsius, and then flowed back into the hot tank. During power generation, the heat was transferred to water to produce steam that drove the turbine, while the cooled salt returned to the original tank. Finally, 46,000 tons of salt were melted in batches, while the pipelines were preheated to prevent solidification. Cerro Dominador's thermal storage system was ready for operation. Once all components were completed, Cerro Dominador entered the commissioning phase. More than 10,600 heliostats were divided into separate zones and sequentially reflected sunlight toward calibration targets on the tower. Cameras recorded the reflected spots, while software measured deviations and sent adjustment commands to the motors of each mirror. Once the required accuracy was achieved, part of the heliostat field was directed toward the receiver, while thermal cameras monitored the energy distribution. At the same time, molten salt was pumped through the system at a low flow rate, and the valves were opened sequentially to control temperature and pressure. Once the circulation loop stabilized, the heat generated steam to drive the turbine, and output was gradually increased to 110 megawatts. Finally, the generating unit synchronized with the Chilean power grid, and Cerro Dominador officially entered operation. Cerro Dominador introduces a different approach to solar energy, capturing sunlight during the day, storing it as heat, and releasing it according to the needs of the power grid. As a result, electricity generation is no longer strictly tied to the hours when the sun is shining. The project's greatest value lies in coordination. The high-rise structure must meet optical requirements, the heliostat field must maintain precise orientation, and the control system must simultaneously balance thousands of reflected beams. Below, molten salt continuously carries energy through a network of pipelines, valves, and heat exchange equipment. But this model is not suitable everywhere. It requires large areas of land, strong direct solar radiation, and mostly clear skies. Construction costs are high, operation is complex, and desert dust forces the heliostat field to be cleaned regularly. Heat is also gradually lost, while the salt must always be kept above its freezing temperature to prevent the pipelines from becoming blocked. Cerro Dominador is not yet a global solution, but in the Atacama, the project has proven that sunlight can be captured and called back after sunset. If Cerro Dominador transforms sunlight into stored thermal energy to generate electricity after sunset, then Berkeley Solar Precinct is opening a new energy frontier in the heart of Australia. If viewed from above the inland region of the Northern Territory, you would see that the starting point of the entire project lies in an area with almost no major cities, no industrial infrastructure, and very few people living there. This is the Berkeley Solar Precinct, the energy heart of the Australia-Asia Power Link. The complex is planned to cover more than 12,000 hectares of desert land near Elliott and Tennant Creek, located in one of the regions with the highest levels of solar irradiation on the planet. Once operational, this area alone could provide around 6 gigawatts of stable, clean electricity, enough to become one of the largest solar power plants ever built in Australia. And to transform an almost empty region in central Australia into a gigawatt-scale power generation complex, engineers first have to solve a critical challenge: deploying millions of solar modules using industrial-scale installation methods never before applied at such a massive scale. In fact, the original plan was even more ambitious. During the initial proposal stage, the design capacity was once targeted to reach as much as 20 gigawatts, equivalent to the combined output of dozens of large-scale power plants. Although the scale was later adjusted after the project's restructuring process, the Berkeley Solar Precinct still retains its role as a power station in the desert, supplying the foundational energy source for the entire transcontinental transmission system. However, building a gigantic solar farm only solves half of the problem, because without a sufficiently large storage system, the project would not be able to provide stable electricity around the clock for Darwin and Singapore. To solve this challenge, the Australia-Asia Power Link integrates an energy storage complex with a planned capacity of approximately 36 to 42 gigawatt hours, making it one of the largest electricity storage systems ever planned in the world. To put that into perspective, this figure is more than 150 times larger than the Hornsdale battery system in South Australia, which had long been considered a symbol of grid-scale energy storage technology. This battery system is placed directly beside the Berkeley Solar Precinct and operates as an intermediate energy buffer layer. During the day, surplus electricity generated by the solar panels is charged into the storage system. When solar radiation decreases or disappears at night, the stored electricity is discharged back into the grid to maintain stable transmission capacity across the entire route. After electricity is generated and stored at the Berkeley Solar Precinct, the project must construct a high-voltage transmission line stretching nearly 800 kilometers to connect inland Australia with Darwin. This energy corridor will transport gigawatts of power from the desert to the northern coastline. Part of this electricity will be supplied directly to Darwin and the Middle Arm region, which is being planned as a new clean energy industrial hub for northern Australia. The remaining power will continue its journey offshore. At Darwin, a large-scale HVDC converter station will be built to carry out a critical transformation step, converting alternating current generated by the solar farm into high-voltage direct current. This is a mandatory requirement for reducing energy losses when transmitting electricity across thousands of kilometers beneath the ocean. After this conversion process is completed, The electricity will be delivered to the Land-Sea Transition Facility northeast of Darwin, where the overhead transmission system connects directly to the subsea power cable route, stretching more than 4,300 kilometers. Preparing for the most complex stage of the entire project, the transoceanic energy transmission journey. Returning to Cerro Dominador, this project in the Atacama Desert has demonstrated that solar power can extend beyond the limits of daylight, but keeping sunlight generating electricity after sunset required engineers to overcome a series of challenges involving structure, mechanics, heat, and precision. From the foundation in the desert, the tower rose upward, the receiver was lifted from the ground, the heliostat field gradually expanded, and molten salt began carrying energy through the entire system. Every stage demanded almost absolute coordination. Can towers like Cerro Dominador become the future of clean energy, or are they only suitable for a limited number of special regions around the world? Leave your thoughts in the comments, hit like, and follow Mandarin Tech to continue exploring the projects shaping the future of humanity.